Good afternoon. Welcome everyone to our third and final webinar of the Future Threats series. My name is Xiaobo Tian. I'm serving as your moderator today. I'm going to spend a couple minutes just to give a quick overview of this webinar series before I introduce our panelists today. Then we will let every panelist spend a few minutes, share their perspectives on this topic, and then we're going to move on to Q&A. The purpose of this webinar series is to explore grand challenges for assistive fabric-based wearable devices across different domains, including movement assistance, training, work safety, sports, space exploration, and other applications. We recognize this is a huge challenge. Recently, a group of researchers at a few different universities got together and discuss the idea of these challenges. As a result of these discussions, we decide to put together this webinar series to bring together experts from all over the country and all over the world, people from different sectors, academia, companies, and some agencies. So our first webinar, which took place 2 weeks ago, was focused on the topic of rehabilitation and assistance. And the second webinar, which was held last week, was focused more on applications related to the future of work. So physical labor, workplace safety, and accomplishing skilled tasks, and along those lines. The webinar today will focus more on sports, extreme levels of performance, and resilience and recovery. There will be a link, maybe Tanya can put it in the chat, where you can access the archives of this series, including, I believe by now, the recordings of the 2 previous webinars. You will also have opportunity to complete a form there, a Google form, to continue the discussion with us or the panelists. So let's move on with today's topic. So again, my name is Xiaobo Tian. I'm MSU Research Foundation Professor and a Rich M. Han Endowed Chair in Electronic Computer Engineering at Michigan State University. I'm moderator today. Our panelists will include Lucy Dunn. This is in the order of presentation. Lucy Dunn, Max Donlan, John Mercer, and Dean Jackson. So I'm going to stop sharing while Lucy can get ready, while I'm going to give her a longer introduction. So Lucy Dunn is a professor in the Department of Design, Housing, and Apparel in the College of Design at the University of Minnesota. She is co-director of the Wearable Technology Lab. She is also co-author of the book, Functional Apparel Design, From Sportswear to Space Suits. Her research is focused on wearability and garment-based wearable technology, and explores new functionality in apparel, human-device interfaces, production and manufacture, and the human factors of wearable products. She has received the National Science Foundation's Career Award and the NASA Silver Achievement Medal for her work with functional clothing and wearable technology. Lucy, thank you for joining us. The floor is yours.
Hi, thanks for inviting me. Happy to be here. I know I have a very few number of minutes here, and I'll try to be quite concise if I can. Not my strong suit. But I wanted to run through a few examples of the kind of work that we do in the lab, and then pose a few challenges that I think are really, some of the biggest obstacles we have in this domain right now. And I'll note that I'm speaking on behalf of myself and also my co-director of the lab, Brett Holtschuh. And if you want to learn more about the lab, the website is there at the bottom of the slide. Okay, so starting out with a few examples. I'm going to start sort of the farthest from sports and move in, although this one is not unrelated to sports. One of the areas that we've looked a lot at recently is understanding the microclimate around the human body, both from a modeling perspective, so trying to understand how we can predict thermal comfort by not measuring the body directly, by measuring the clothing, the temperature of the clothing, so you don't have to wear sensors against your skin, basically. And then how we can mediate that microclimate to improve human performance and comfort in cooler climates. Specifically, we're focused on heating. So that you'd be willing to turn down your thermostat in the winter. We can save some energy and make everybody in a shared space happier and more productive. We've also done a lot of work on sort of closed loop sensing and actuation on the body. And this is one example, and I'll give you another one in a minute. This project was focused on trying to support mobility, upper limb mobility for children who are born with a mobility impairment. So in this project, we're looking both at trying to sense the position and movement of the body with some specificity through soft sensors, and then trying to actuate or support that movement, again, using soft actuators. So the actuator component is hybrid. It involves a pneumatic bladder that does the abduction or the flexion extension, and then shape memory springs that do abduction adduction movements. We've also looked at accessibility in clothing from, sort of multimodal domains. So this project was looking at trying to apply therapeutic compression for sensory processing disorder. Brad's specialty is in shape memory alloy and garments that sort of mechanically actuate. So you'll notice a theme as we go along. So this was focused on trying to calm the nervous system by applying pressure in a way that's less obtrusive, less bulky, and more dynamic than current weighted garments or compression garments. Again, in the accessibility domain, this was a project looking at how, it's an ongoing project actually, looking at how we could improve accessibility of clothing to enable people with mobility or dexterity limitations to, better achieve activities of daily living like dressing. So the shoe on the left has an actuator that contracts the fastening mechanism, and then it latches with a magnet so that it would hold that compressive force. And then the bra, again, similarly, is a bra that you could put on quite loosely fitting and then have it actuate and compress around the body to create that tightening force. I know we have a space influence today, so I'll run through a few examples of some of the space applications we've worked on. I don't know if you can see my cursor. This is the liquid cooling garment. That's the sort of base layer of the spacesuit. It's a garment that was designed in the 60s and really hasn't been touched since then. And if you know the history of the spacesuit, it was designed in an emergency. This was not a long process, a careful process. So it has a bunch of tubes that run through it that run cool water around the body. And the placement of those tubes was not sort of carefully designed. And as you can see, the way that they're oriented, when the body moves, they tend to sort of gap away from the body, which really affects the efficiency of the cooling of the system. So we've worked a lot on sensing that, so trying to be able to measure when the garment is touching the body or not. And then in the middle here, this was a solution that we developed, a tubing layout that follows Iberol's lines of non-extension. So it in theory should be much more mobile and stay close to the body during movement. We've also looked at spacesuits touching the body in a lot of different domains. Spacesuits do a lot of damage. They're not fun to wear. If you wear them, you come out with injuries pretty much always. And so things like rotator cuff injuries are very, very common in astronauts because of the time they spend wrestling this suit during training. And it's really hard to measure because you can't see inside the suit. And if you put sensors in there, they often start making things worse. They make pressure points, they make abrasion points. So we developed these leggings that you can see under the mock-up of the hard lower torso that are textile based, and they're conformal. And we looked at trying to use those textile sensors to detect when and where the rigid portions of the suit were touching the body. And then we were also trying to explore the feasibility of actually measuring pressure, which is really, really hard to do on the body. Speaking of, this is one of our most recent and most advanced approaches to measuring pressure on the body and also applying pressure on the body. This is a spring example, but we've also done the same thing with a knitted shape memory actuator. So this is closed loop compression, where we're modeling both the soft sensors, which are full of error, and the soft actuators, which are full of error, and then using control models to be able to create consistent forces that are applied to the body, and allow those forces to be dynamic so that you could move pressure as it moves over the body. This is important to space because one of the really exciting alternative space suit concepts is mechanical counterpressure, where you have this loose fitting garment and it compresses around the body instead of inflating air around your body. And again, being able to control that is something absolutely vital. You need to be able to apply the correct amount of pressure so that the crew member can still perform their functions and is still comfortable, but it's going to stay alive. And we've looked at some other low-tech things like socks. When you spend a lot of time in space, you come back with calluses on your feet because on the tops of your feet from holding yourself against these bars while you're doing work. So these are gripper and hook socks that allow you to not injure your feet while you're moving like that. Okay, first challenge, comfort and accuracy tend to be almost opposed in garment-based wearable systems. So we're always trying to overcome accuracy challenges while preserving comfort. Another huge challenge, sizing and fit. I don't know if any of you have tried to develop a precisely fitted garment and then put it on someone else. Really, really hard to do. And we've had students in the lab that have done a lot of work trying to measure that kind of sizing challenge and also trying to overcome it with optimization processes for sizing systems. And I can talk a lot more about that. This is a solution we've explored, which involves plug and play components. So we have this textile backbone that we can attach components to anywhere we want, which allows you to be a little more adaptable about that fit. Another challenge is prototyping and manufacture. Those of you who are in industry probably know this very, very well. There's very little infrastructure or supply chain in our domain, and we're constantly inventing new methods. We've looked a lot at trying to use the tools and techniques of cut and sew industry, the existing cut and sew industry, and try to adapt those to e-textiles. And then lastly, social factors cannot be overlooked. Google Glass is a good example, I think, of where we overlooked some social factors or got them wrong, and consumer adoption really suffers. So I'll leave it there.
Thank you, Lucy. It was so impressive to see the array of different applications you talked about: thermal modulation, accessibility, space applications, and also amazing set of different things like different garments, from socks to pants to other parts of the basically the clothing. So thank you very much for sharing. We're going to come back to discuss some of the topics you mentioned during the Q&A session. Our next speaker is Professor Max Donnellan. Max Donnellan is a professor of biomedical physiology and kinesiology at Simon Fraser University in Vancouver, British Columbia. He has a PhD in integrative biology from UC Berkeley, and he did his postdoc in neuroscience at the University of Alberta. He studies how people and other animals move and then apply the findings to help the society. His lab mostly studies walking in people, with a focus on fundamental things about the back and forth relationship between how we walk and the energy we require to do so. He also studies big and small animals and how their size affects how they control their movements. Max.
Thanks so much, Sabo. And that was fascinating, Lucy. I really enjoyed that talk. I thought here for future threads, I'd focus not on some of the work we've done in the lab about particular wearable technologies, but instead tell you about a new initiative that we have that addresses what I think are two important principles or challenges for wearable technology. First is that you need to really do human-in-the-loop design and testing. This is not just human-in-the-loop as my colleague Steve Collins and Dave Remy might use it, where they are tuning controllers in an exoskeleton. But I mean this more broadly, where when you're designing things that people are going to wear, you need to be able to rapidly prototype, put them on people, and have them try them on in realistic environments and iterate over and over again. And that can be slow, especially if you are a lab that just does the prototyping and not the testing, or just does the testing and not the prototyping. And what makes it slow is we really don't have a good predictive simulation of what a human is like to design with. We don't have a solid works of the human body. And so we must do this iteratively. And so it's helpful to think about processes and facilities that make that possible in order to advance more quickly. The second thing is that we really need to combine university and industry efforts, not just a collaboration, but kind of a mashup where you work closely together. Often what can happen is things happen in a university where something gets invented and then licensed and then hopefully picked up by industry. And that's a tried and true process, but it can also be quite slow. And a lot of the textile-based research is done in industry and would be beneficial to have that tight collaboration between university at the same time. And so with those two ideas in mind, here at SFU, we've been working on a project called WearTech Labs, which is a $20 million investment from SFU and the Canadian government into this 10,000 square foot R&D facility for wearable technology. And it reports up all the way up to the top rather than into an individual faculty. It has dedicated staff for work currently that are trained well and hopefully will stay with us for their careers, and which means that they have a different value proposition than graduate students that, we, by design, we're trying to get out of our labs. And it's, the way that WearTech Labs is supposed to work is both with academic and industry labs and move at industry speeds. And to accomplish this human-in-the-loop design of wearable technology. And so for prototyping, we have pretty amazing 3D printing capabilities for metal and plastics, as well as smart textile labs that can sew and knit and make garments. We can print electronics onto fabrics, and we can then characterize them with materials testing machines and rheometers and scanning electron microscopes to see how they break or whether they're performing the way we want them to perform, etc. And the human in the loop part is that we also have kind of standard biomechanical motion capture facilities that allow us to measure things like muscle activity and forces and motion and energetic cost. And we have upper body related equipment as well. This is a kin arm, which is a robotic manipulandum that's useful for studying how the arm moves in healthy people and after stroke and things of that nature. And then the latest part that's coming online this summer, and the renovations in full swing, is a facility that's meant to simulate basically any environment that you might experience on Earth. I hadn't really thought about space applications, so maybe Lucy, you want to tell me whether or not we're going to get there. But it includes an environmental room, which can go down to -50 and up to +50 degrees Celsius. You can change the relative humidity between 0 and 100%, and you can change the level of oxygen down to Everest levels. And it's next to a sleep room, which is designed to run sleep experiments for a couple weeks at a time. And this also is an indirect calorimeter, so we can measure people's calorie consumption, their energetic cost, without attaching a mask to them. We can sample it directly from the room. And the thing I'm going to have most fun with, I think, is a wind tunnel, which has the floor is a treadmill, and it's not the kind of wind tunnel you'd use for like aerodynamics of sports cars, but instead for simulating the wind that you might experience in a run or a bike ride or when you're mountaineering or what have you. And also in that chamber is lights that simulate the solar radiation you would get on, basically anywhere on Earth. And so we're trying to get to be whatever you might experience. And then finally, a hearing room, and where we can control the environmental noise. So these put together allow us to rapidly prototype and test wearable technology with staff that their mission is to work with industry and academic labs on their ideas and their projects. And I think this is like more of a process that will help advance future threads. That's my spiel.
Thanks so much, Max, especially for sharing this novel paradigm of collaboration between industry and a university, and also very amazing setup you have there. Congrats. All right, our next speaker is Professor John Mercer. John Mercer is a professor in the Department of Kinesiology and Nutrition Sciences at University of Nevada, Las Vegas. His research focuses on human locomotion and sport performance, with a focused line of research on biomechanical and physiological response during locomotion. He also has a research focus on sport performance using wearable technology devices in the field. He established the Biomechanics Laboratory at UNLV, and he is a fellow of the American College of Sports Medicine. Thank you for joining us, John.
Thanks so much. Boy, I'm already enjoying this webinar. And first, I want to give a shout out to students, because I know part of the NSF project that is being worked on is workforce development. I want to speak a little bit about that because what we're doing here at UNLV is we are close to launching our new PhD in sports science. Hopefully we'll take students starting fall 2026. And really we're taking the direction of trying to train the next generation of sports scientists. And with sports science, what we're doing with our students is teaching them the scientific method applied to sports. So how to use science as a way to help sport in some capacity. And so we collect a lot of information, all different types of sensors, wearable, non-wearable. We have a bricks and mortar lab that we were able to do kinematic analyses, kinetic analyses, muscle activity, what have you. So we get a lot of information, but then we try to teach our students to take the information and generate knowledge. And so that's a nice little gap there. And so what is sports science? This is a phrase that's used to mean a lot of different things, and a lot of different professional teams, college athletics, they hire sports scientists, and they all mean something a little bit different. And there's all different types of words being connected with sports science, from sport analytics, sport performance specialist, and what have you. Well, what I do is I talk about sports science through two different lenses. The first lens is, how do we use science to help people in sport right now? So how do we help an athlete? How do we help a coach? How do we help a team with science applied to whatever sport it may be? And maybe it has to do with preventing injury or rehabilitating from an injury, learning a skill, or just being, developing strength and endurance. So that's one lens. The other lens is, how do we generate new knowledge? And so this is the type of research that our tenure track faculty are working on, our PhD students, our master students, working on developing projects that develop knowledge down the road. And these are not necessarily the same people doing each of these types of work. For example, when we work with a team, the coach wants the information right now, and they want it in a way that's going to help their athlete immediately, or as soon as possible. Whereas when we do a research project, as those of you on this call know, we start a project, and maybe 6 years later we actually publish and share the data. That's not going to help our athletes. A project that Dean, who's next on the list here, helped me with was doing core temperature while swimming in wetsuits. And we started collecting those data probably 6-8 years ago, and we really just started publishing some of the results now. And so it takes a long time to generate the knowledge, and take several iterations of experiments to ultimately take the information and then generate some type of knowledge, mechanisms of injuries, evidence-based practice, what have you. And so that's my approach to teaching and research. And when looking at sports science, what's nice is to sort of categorize athletes in different buckets. And this is a model put forward already. But it's a nice way to approach sports science, because what we're trying to do is move athletes to the healthy high performer. Now, when I say athletes, I don't necessarily mean just Division I or professional athletes. I mean age group athletes, people who are just trying to complete a marathon, mere mortals, if you will. And so really we have sort of 4 quadrants of performers: healthy high performer in the top right, healthy underperformer, unhealthy underperformer, and unhealthy high performer. Now, we have to contextualize some of this in terms of what do we mean by healthy? Is that a physical health or is it a mental health? Those both apply. And even with performance, are we talking about, winning a 5K, or are we talking about completing a 5K? So often I talk about athletes being competitors or just trying to complete an event. And we have, hundreds of thousands of people who just try to complete marathons or Ironmans or what have you. And so ideally, we are trying to move people up into a healthy high performer, whatever healthy means and whatever performance actually means. And so in the context of the wearable technology, this is what I look forward to: a lot of the wearable technology being developed to ultimately help move people into that top quadrant. So this is just sort of big picture approach in terms of how I approach research and teaching. When I look at human performance, I really look at a very simple model of human performance. And that model is that we take chemical energy, potential energy in the body, our carbohydrates, our fats, maybe a little bit of proteins, and we transform that chemical energy to mechanical energy. Very simple model, but we generate forces and we generate movement. And the process of transforming that energy from the chemical to mechanical is largely a physiological process, aerobic and anaerobic pathways. Yes, it's a little bit more complex. There's springs that are involved in elastic material, but for simplicity, this is the way that I look at human performance: is we're trying to take that potential energy in the body, transform it either using oxygen or not using oxygen, or both most of the time, and generating mechanical energy that allows for movement. And so when I teach my classes, actually one class is focused on physiology of endurance performance, where I'm really tackling this left side of this model, and the other class I teach is biomechanics of endurance performance, and I'm more on the right side. I put this up, and I thought this would be good to share in the context of wearable technology, because ultimately when we're looking for a smart fabric or smart garment, we're looking to sense something in this sort of model of transforming chemical energy to mechanical energy. And then with the robotic part, or the assistive part of the wearable technology, we're trying to generate some type of force to ultimately assist something. And the trick with this mechanical energy on the right is not only are we trying to generate force, but we got to generate the right amount of force applied at the right time and in the right direction. And so there's a bit of coordination that's involved with that. And I've got this little box down here: injury happens when we do too much too soon, or too fast, or change something dramatically, and ultimately we have some type of injury that typically shows up. So in terms of the research I do, I really put it in 2 different bins. One is an applied bin, and I got into this area of exercise science, sports science, because I was training for triathlons and competing back in the 80s, and I discovered how you could test different aspects of performance. And that just grabbed my attention and took me all the way through to where I'm at now. And so I like to ask questions I want to know answers to. I still do triathlons and still want to know what's the best wetsuit to wear. This is how I connected with Dean, who's going to be the next speaker. And I've worked, Dean invited me to go along with some of his research team looking at measuring drag forces during swimming. We've done some muscle activity while swimming in the water. We've done some core temperature swimming in different wetsuits in warm water in particular, and done some things like swimming economy, both in the water, and some work simulating swimming on land. And then in terms of wanting to know more about how to do better in endurance performance, I've also done work in transitioning from swimming to biking. And then in the biking world, worked, again, this is Dean's sort of masterpiece here, looking at some heated garments and the influence of heated garments on cycling performance. We've also done some things like measuring drag forces, some cycling economy. We've measured accelerations and vibrations of bikes in order to understand rolling resistance a little bit more, and have worked with another company on the influence of wheel design, tire pressure, and tire type, on factors like rolling resistance. And then I also do a lot of work in the running space, mostly with body weight support at this stage. I've done a lot of work with running in the water, looking at EMG, muscle activity, energetic cost of running in the water. And then probably in the last 10 years or so, really moved to working with a body weight support treadmill, lower body positive pressure treadmill, where we've done a lot of work with EMG, trying to understand how people run, how they adjust their gait with different levels of body weight support. The other bit of research I do is more sort of conceptual, theoretical, and I ask the question, why do we run the way we run? Sounds like a silly question, but I always pose this to my class. I say, you may see a friend running or walking towards you. You don't have any ability to do any facial recognition, but you can see them and see the way that we're moving, and you know who they are. What happens is we have this movement fingerprint. We move uniquely to ourselves. And this is just a video of back in the New York Marathon, that if we watch running, and running is one leg in front of the other type of thing, very characteristic movement. But if we start looking at elite runners, and these are all elite runners, they all have very unique running styles. Some of them are very different, and some have nuanced differences. So why do we have a particular running style? And what are the factors that go to me choosing to run a particular way? And so this is just a slide, again, in terms of the complexity of a smart assistive wearable device. Running, swimming, biking, why do we run the way we run? Why do we swim the way we swim? Or why do we bike the way we swim? It takes a lot of coordination, and we have to have perception of what our environment is, how we're moving. We have to predict what's going to happen when I put my foot out in front of me. Is my foot going to be landing on a stable surface or an unstable surface? We have to then coordinate different muscles ultimately to move a limb into a particular position. And then for running, we have to do this adjustment 5,000 times in 30 minutes. And so it's a constant iterative process of successful running. And if we choose the wrong movement, we coordinate things incorrectly, we have an error in performance, which could be a slip or a trip or what have you. And the environment that that running happens, or any movement, does play a factor in ultimately determining how we're going to run. And so I think that's going to be a challenge with the wearable assisted technology, is also incorporating the environment and some of the goals that someone has for the activity. And finally, I thought I'd put this up because I think it's relevant for wearable technology and development. Is we've recently launched a mobile lab that we're taking sports science out to the community, and we do demonstration for K through 12, trying to introduce people, students, to different sports science careers. Not just being an athlete, you can pursue other ways to be involved with sport from a STEM perspective. And I think I'll stop there.
Thank you very much, John. Appreciate sharing your experiences in not just research, but also teaching and outreach, and also appreciate your discussion about the interaction between the human movement, the environment, and these wearable technologies. And that's a really good segue for our last but not least presenter, Dean Jackson.
Good evening.
Sorry, Dean. I need to give you an introduction. Sorry, because I was looking up my notes here. Dean is a sports industry leader who founded the premium endurance sport apparel company Hope in 2012. Hope takes its name from human movement specialist Professor Hope Toussaint. Dean founded the Hope brand after 3 decades of experience in the endurance sports and the marketplace, in the endurance sports marketplace. He originated in the swimwear and the triathlon categories, and now embraces all endurance sports. Its products combine research, science, and reality. Dean, floor is yours.
Thank you. Do forgive me for not having a presentation ready, but if you don't mind, if I could just talk through some of the projects that we've undertaken and some of the challenges that we've faced. I do feel very unknowledgeable and underfunded when I see some of the incredible projects that you're working on. I need to get a very quickly over to see this incredible lab, Max, that you're working on when that's ready. From an industry point of view, to have that facility on hand, for me, only really exists with the top 10 sports brands, or a sports brand that certainly owns a niche. If you're outdoor clothing and it's cold, super cold weather clothing, that's all you do, you may have the ability to really focus in. In my world, I come from one of the most laggard industries, which is wetsuits. And I will speak also for the surfing wetsuits within that. When you look at the changes within the industry and even the materials, it stayed exactly the same for 30, 40, 50 years. And you know, from first DuPont developments to what we have today. Our task that we set ourselves as a business is to use research, science, and reality to find and search out the problem, because there's nothing better from, let's be honest, a sales proposition as to creating the problem and then solving the problem, even if we didn't know it existed. So we'll research what the market needs, or what the market thinks it may need, or even doesn't know it needs, and then use the science. We're working with John, we've worked with Nottingham-Trent University, and we work with some very smart individuals who are actually in the sports field to come up with the solution. And then, of course, the reality, a bit like your Google Glass, is there really a market for it, or are gold-plated goggles actually necessary in the marketplace? As we move through our industry, we started with wetsuits, and exoskeletons was something we really wanted to look at, but to play with, we just have materials and we just have modulus. But the key for us is, how do we test that? So as I say, from an industry, we don't have bits in place that we can pull on and pull all these wonderful ingredients together. We set out to, with Professor Hu Toussaint, create our own measurement of active drag, which is a $300,000 investment with 17 force plates on a 25-meter pool. It would allow us to play around with different materials in a composite neoprene world and understand if they were delivering benefit to swimmers, even down to the fact that women float very differently to men. Can you believe our industry wasn't even looking and recognizing this? And we took that to the next stage of exoskeletons to put controls in, looking at the environment. And when you're suspended in water, it's very, very different than having a touch point with the ground. So we were trying to put controls into a wetsuit, but also change the way that swimmers were thinking about their swimming. And when you put someone in a suit that has great controls in it, you're taking them out of what is believed to be and what exists within their marketplace and what they're used to. But we had the testing ability to be able to do that, and found some incredible results off the back of it. To take that into manufacturing, which those that are looking at this will be aware of, has its challenges as well, because an industry like ours, certainly the sports industry, is wanting big volume, big movement, and can we move this quickly and make a margin? When you're going to the suppliers and the manufacturers, they don't have the R&D capabilities that you would actually expect. When you look under the hood of the sports industry, there's not as much going on as you probably think goes on. It's actually when you are in it that, again, I go back to my first point, it's really the top 10 that are really actually driving it. But as we progress through wetsuits, we wanted to start looking at dry land. And for us, it was important how we manage heat from wearing a neoprene suit, which has its own microclimate when you're looking at the neoprene in the skin. And then you're stripping off, and then you have wind chill and you have other factors that are affecting the athlete. So suddenly you have huge temperature drops. So we've worked on different types of fabrics that perform differently at moving heat, but also shielding the body at the same time, because you're going from taking off a wetsuit that gives protection to riding at 30, 40 kilometers an hour in 10 degrees of wind. That can certainly cause hypothermia because you're cycling too fast, which sounds a bit bizarre. But that was some work that we did with the Norseman triathlon, where we had to look at how the fabrics, as they perform very differently, and were a dual purpose solution. As a company, we then felt very lucky with a cycling team that we worked with, that were 4 incredibly smart athletes that wanted to challenge the status quo of an event, which was the team pursuit in the velodrome. If any of you have seen that, 4 riders either side of the track, the gun goes, you try and catch them up, and the first one over the line wins. We worked with a group that changed not only the way the event was pieced together and the typical format of changes of those cyclists, but looked at every single element of how you could improve performance. So they weren't funded by a governing body, they were funded by a small company in the UK, which was ourselves. And one of the key areas was warm-up, and how we could use fabrics and heat to almost enhance the active warm-up through deep muscle heat. And we created some heated garments that were originally developed by Adidas, but took it to a new level. And we supplied an incredible amount of athletes at the Olympic Games Tokyo, the Olympic Games in Paris, teams that we can't talk about because we didn't pay enough money to be able to talk about it. And we're now working on a project with a global patent company called Haydale. We're using graphene. And we're attaching the graphene to the fabric. It's not knitted into the fabrics, but again, that comes back to the other challenges of how do you get the fabric mills and how do you get your assemblies and your cut and sew manufacturers to start thinking of flat printing graphene. And it's a print, it's an ink that is printed onto a fabric panel. Then the current is passed through it and you're up to 52 degrees instantly. And we don't, our research is telling us that we've done with John, we don't have to prescribe an active warm-up. Suddenly we can have athletes ready to perform without doing some of those silly warm-ups that you'll see soccer players doing up and down the side of the pitch and focusing on the game. 20 seconds of putting some tension into the muscles is all we need. This is another area we're working on at the minute, is how we can put graphene and currents through a garment. But again, it keeps bringing us back to legislation of governing bodies, ability of factories. And when I go back to legislation of governing bodies, the world of swimming has taken many steps backwards. I was involved in the suit wars where certain brands made certain claims. And then when other brands came up with those same claims, suddenly those claims were pointless and worthless and detrimental to the future of the sport. Even the fact that in sport now, we're not allowed to work with a zip on a women's suit on poolside for FINA competitive swim events. So that's taken away some of the options to play around with tension and fit. It also has challenges for some of the athletes of when they're putting their suit on and decency around suits. So we're constantly fighting a battle of what fabrics can do, how we can integrate that into the marketplace, integrate that into the product, and also be very aware that any investment in this area in sport could very easily be quashed and killed overnight by a governing body in Switzerland that just doesn't like what's going on. So yes, that's us. That's a little bit of what we're doing. So again, apologies for lack of presentation, but I'm here in awe of the capabilities of, goes back to Max's point of when industry and learning facilities and education can come together. We found, just by working with John and the Nottingham Trent University in the UK, that the rewards can be massive, and in an industry that sometimes is very laggard, really can give a massive leg up.
Well, thank you, Dean, for the actually fascinating sharing of your particular insight from industry side, from the angle of the industry, and really amazing stories about, you know, involvement in these really high stake competitions, right? Really Olympics and things like that. So now we're moving into the next phase of the webinar, which is Q&A phase. So audience, please put your questions in the Q&A section of the Zoom. And in the meantime, I'm going to start off with some questions that, you know, by listening to these presentations. So maybe just building off what Dean, you were talking about in the sports domain, when you have these smart kind of garments or assistive sort of wear, what is allowed exactly? Because I heard that clearly you can do active thermal management, right? Like active warm up, and no, of course, people design these suits to be like passively more hydrodynamic efficient and create less drag. How much is allowed, for example, when you have active mechanical assist, like, because when we talk about these actuation, make compression and other things. And of course, you mentioned the danger of these governing bodies at any moment can make a call on what is allowed, what is not. So what is the general kind of, in this particular space, for assistive fabric, what is the limit here? Or what are the limits that people in the industry or in the space will have to be aware of?
I think in the industry, the limits of what can be created is down to those that are like the collective that we have here, and the imagination, the capability, and especially when you have what Max is looking at, where you're going to start knitting your own fabrics. The problem we're always going to have, that's going to be the threat, and very high on the risk register, is that the governing bodies will only react to what is presented to them or what is seen as a threat. They don't know what's coming. They don't know what might be down the line. We certainly can't be putting dials onto swim skins to make them tighter and put controls into different parts of the body. There's challenges ahead. We work in cycling, and where we have double layered fabrics, and we're the only company that produces a triathlon wetsuit, a tri-suit, sorry, that's based around the speed of the athlete. Every athlete has a drag crisis. Not every athlete's going the same speed, so we're trying to bespoke that. I would love there to be some mechanical way of where you can change the ridges of the fabric, or they rise or they fall depending on the speed of the rider, and we could spend millions developing that. But as soon as a governing body, who a lot of the time are very ill-educated old school blazers from within that sporting industry, or just athletes themselves, they can put a quash on it absolutely overnight. Their management, their policies are very biased towards the governing body, and it's not open content. And we have to work very closely with the World Federation of Sporting Goods International, which is a mouthful in itself, but they lobby on behalf of the industry to try and help push development. As soon as we have smart fabrics in the arena, you will have an immediate pushback against it. And certainly if it's coming from more wealthier nations that will be able to afford the partners, or have bigger partnerships where this funding is available, the smaller ones will soon rise up. And all these committees of the governing bodies are made up from nations from all over the world. So a very, very long answer to say that there are no boundaries for it or rules set for it, but someone will set a rule as soon as it's there to try and quash it, unfortunately.
Yeah, that's fascinating. Fascinating. Max.
Yeah, and for sports that are competitive, like triathlon, I mean, but Dean, I couldn't never argue with your experience in that. It makes total sense. But there are some sports like mountain biking where half the bikes on the trails now are electronic assist. And it's not because they care about being competitive, it's because they care about accessing different terrain that you can't get to if you have to pedal yourself. And I wonder if surfing might be an opportunity too, where the demand is less about being competitive in a competition and more about the experience itself. A thought.
Great. Any other panelists want to comment on this topic?
I'll just add in, I think you're spot on in that another work we do is with circus artists, or Cirque du Soleil type of artists. So performing arts, which the key factor there is aesthetics or show dynamics or choreography. There would not be rules in place for that type of activity. So that would be another area for smart assisted garments.
Great. So now I'm going to switch gear to a question posed by Marcy. Many of you are working at the bleeding edge of tech to augment high-performing individuals or to make wearables or garments more accessible to those with limited mobility. What opportunities do you see for these wearable and functional fabrics for the everyday person?
I guess it depends what you mean by everyday person. I mean, we're all sort of temporarily abled. And we will all go through, periods of time where we have various needs for support. I'm thinking of, the increase in conditions like POTS, postural orthostatic tachycardia, I forget all the acronym words, but circulatory disorder where your body's not keeping enough blood in your brain when you change posture. So when you stand up, you might faint. There's a huge increase in that post-COVID because of the vascular changes that COVID induced. So I think there's a lot of conditions that people live with for long periods of time that I think wearables are garment-based wearables specifically are uniquely positioned to help. Because, it's the kind of thing where, if you have something like POTS, you're not going to, wear an inflated garment every single day because it's just too socially obtrusive and too cumbersome. You might wear compressive stockings for a while, but they're really annoying to put on. And, that's when we get into the real, like, okay, we need this to feel like everyday clothing. We need this to be part of our existing routine. And we can do that with advanced materials. We can use shape memory and it's triggered by your body temperature. So you just put them on loosely and then they squeeze and you unzip them to take them off or whatever. So I think there are a lot of opportunities like that where the sort of marginal increase in performance during everyday life is really important. And that might be a good place for wearables to sit because, again, we struggle with garment-based wearables struggle with getting close to like clinical efficacy in some domains because of these things like comfort and accuracy trade-offs. It's hard for us to get medically relevant, but we can get wellness relevant. We can get sports relevant. We can do piecewise improvements until we get closer to some of those medical goals.
Great. Any other? If not, actually, I can move on to the next question. This is from Steve Collins from Stanford. What actuation or sensing capabilities of new garment-based wearable devices would you be excited to make use of in your projects? And what is your honest perception as to how close the state of the art is to being useful for your type of projects?
My type of projects are probably the farthest out. I mean, my job is to be on that end of 20 years from now. So I would say I'm very excited about a lot of different things. Maybe not individual components, with maybe the exception of shape memory, which we do a lot of shape memory, but more the integration of those components. So I think things like closed loop devices that are accurately able to sense and then actuate in appropriate ways. Those are some of the frontiers that wearables haven't really attacked yet. We're more interested in the standalone actuator or the standalone sensor, and bringing those together with a control system is pretty hard to do. So we're starting to delve into things like that. There are areas though where it's very close. Right now I'm working on a potential startup treating neonatal jaundice, and the actuator is a blue LED. Like that's not the hard part. The hard part is the system and manufacturing it and building it into something soft that you can put on a brand new baby that has just come out. So things like that.
Right.
Uh,
Yeah.
So it's a little unfair to answer Steve's question when I can just answer it in an hour when we meet anyway. But to emphasize the excited part, I would like to dunk again. So if you can give me something that is powerful and lightweight and comfortable that would allow me to have superhuman abilities, I want that.
John?
I'll take it from the other end and go to the endurance world. What mere mortals, age group athletes and professional athletes want is the ability to go longer, faster, what have you. And one of the limitations is not physical limitation, but often nutrition and information that they get back in terms of how hard they're exercising. And so my wearable tech future is to have a gas gauge that is sensing everything from blood glucose, maybe some lactate, maybe even sweat, and monitoring intensity of exercise, et cetera. And then in essence, giving you a gas gauge in terms of what should you eat at the next aid station or what should you drink. Because sometimes that ability to get calories in and then use the calories, the ability to get calories in, sometimes that's the big mystery to a lot of these endurance events is fueling correctly.
Right. So maybe I can come back to my list of questions. So I think the topic of sort of synergy or interaction between universities and industry has come up several times in our panel's presentations, and also the issue of education. Clearly, for this emerging field of active assistive fabric-based kind of these devices, there are a lot of challenges. So I know we have already touched upon this topic quite a bit over the past 40 minutes, but maybe I want to see whether folks have additional insight as to how to best sort of foster this kind of partnership. Like, okay, university professors, like researchers, like all of us, some of us here that we have advanced materials, right? And then industry has, of course, their own strength, but they may not have enough R&D. I think the Dean pointed out, or is it Dean pointed out, to do some of these things. So what is the best idea to bring them together and make a sustainable kind of long-term relationship?
I can jump in on that. We've done a lot of interface with industry in a lot of different ways over the last 15 years or so. And as a researcher, our gold standard, our best case scenario is a funded research project where a company comes in with a lot of funding, and we do a year or more of collaboration. That's relatively rare, I find, especially in the apparel domain. It works best with companies that have a big research outfit themselves, and we're interfacing with other researchers. Industry and smaller companies, it's a little bit harder. We've had a lot of success with a mechanism that I founded with partners at Johnson Space Center. We developed we used to call it the Wearable Technology Cluster, and now it's cluster was like an elaborate NASA acronym, and now it's become it's hosted by the Technology Collaboration Center of Houston, and they call it the Wearable Technologies Symposium. So every spring, a class that I teach and other similar classes at universities across the country collaborate with mentors at Johnson Space Center and mentors from industry working on related problems to do semester-long course projects. And that has worked really well to do kind of sandboxy type stuff. Like there's no IP protection because we're going to present in this big symposium, but it's good for stuff that companies are interested in dabbling in or exploring, but they don't want to sink $100,000 of research funding into. So we've done crazy things like self-zipping boots and self-cooling underwear and all different things for a lot of different companies. And that some of that has led to PhD dissertations or funded research projects. So the stuff that has legs kind of goes somewhere. So that's been really useful. And then the other mechanism that has worked well is the government's STTR. So that's like for small businesses, that's a great way to get government funding to work with a university.
Great. Thank you very much, Lucy, for sharing that. We have only 2 minutes left on the clock. I want to see, just go around, see panelists, whether you have some punch point that you want to make. You have not got a chance to share earlier.
Well, I'll start, and I'll just sort of piggyback on what Lucy was just saying here, because I got Dean on here, and Dean and I have been working together for I don't know how many years, and it really takes a lot of trust and understanding on both ends in terms of working industry and academic partnerships. Dean's been very patient. He knows that research takes a long time, and good research is hard to do. Bad research is easy to do and get quick results. And so the ability to work with both academic and industry, it really does take a lot of trust in building a relationship that is a long-term vision.
Thank you, John, for sharing that. Anyone else?
Yeah, I'll take a different tact, which is that I find it helpful to calibrate myself to the complexity and difficulty of the problem, and that wearable sensing is hard, but I think about it like when you are building like a something to measure your blood pressure, right? That's challenging to do. Companies do it. They make these devices that measure blood pressure, and they're very useful for society, but not as useful as drugs that control your blood pressure. And those are much, much harder to develop. And they require clinical trials, and they require discovering new mechanisms inside your physiology. And when we're talking about building devices that not just measure from you, but actually actuate you, control you, regulate your physiology in some way, it's a big challenge that requires human participant experiments, it's going to require some discoveries that are both at the materials, devices, and physiology level. And so going in, understanding it's complicated, like on the level of developing a drug, I think is useful.
Thank you. Thank you, Max. Dean, I think you want to share quickly.
Thank you. I just wanted to pick up on the point of industry working with education again. John and I have a long relationship, but it's also about understanding each other's needs. I've had more success working with a US learning institution than I have a UK institution, because the UK, it tends to have been, apart from Nottingham Trent, what can we get out of it? What grant can we apply for to put into the university? And then we're going to use your name, but thank you very much. We're now going to go off and play with millions of dollars. The partnership with the US has been understanding what both sides want from this, and then finding a project that is achievable so everybody's happy. Some will be short, medium, and long term.
Great. All right. I want to thank all our panelists for your great presentations and sharing your unique perspectives and insight. I want to thank all the attendees for sharing the 1 hour with us. The talk today, this webinar is recorded and it will be shared on the website that I post in the chat space. Thank you again. Bye.
Thank you, everybody.